got a couple of lines. I'm just going to write them in like column form. So we're going to get 1 minus 2, 3, plus lambda times 2, 1 minus 4, and 5p minus 7 plus mu 6, 1, 8. Lambda and mu are scalar parameters and p is a constant. Remember what this line is doing? Just want to remind you, we start at O, we get onto the line using the first position vector. And then the second vector is like our direction vector along the line. And we're going some multiple of it. So if you want to get to here, you'd maybe double the position vector and so on. And that will get you anywhere along the line. Now we're told, sorry, that the plane pi contains L1 and L2. Here's my plane. We got L1 here, for example, L2 here. Not sure exactly it's going to look like. That's a little sketch. And we're asked to show that 3 minus 10 minus 1 is perpendicular to the plane. So what we can do is find the dot product with each of the position vectors, because remember, sorry, the direction vectors. The direction vector will be in the plane, this one here, and so will this one. So let's do 3 minus 10, 1 dotted with 2, 1 minus 4. And we don't need to use like the cos version or anything. We're just going to dot it. If we get 0, we can say it's perpendicular because it will mean that the angle's 90. So 6 minus 10 plus 4, we get 0. So therefore, perpendicular to L1. And in a similar way, I'm going to do 3 minus 10 minus 1 dotted with 6, 1, 8. And that's going to give 18 minus 10 minus 8, which is also 0. So therefore perpendicular to L2. And hence 3i minus 10j minus k is perpendicular to the plane. It's enough to say that because it's perpendicular to both of those lines, it must be perpendicular to the plane. Let's determine a Cartesian equation of the plane. Now, because of what we've just shown, we've actually found the normal vector to the plane. This thing here is n. And what we can now use is the normal form for the equation of a plane. And it's that r dotted with n equals a dotted with n, where r is our position vector x, y, z, n is our normal, and a is any vector that gets us into the plane. I just want to show you where that comes from. I just always like to do these little detours, and then I'll get back to the question. But let's say we've got the origin here. We can get in onto the plane using a, but we could also get onto the plane using r. This is our general now position vector that gets us anywhere in the plane. A is a specific one. And then I could construct r minus a here. But I've also got my normal vector. Now, as we kind of showed in the previous part, r minus a is in the plane, and therefore if you dot it with n, you're going to get 0. And you could just rearrange this. So you could use this form if you wanted, but yeah, it's going to be that you can actually kind of multiply the bracket out. We haven't really shown why we can do that, but we can. R dotted with n is then going to equal a dotted with n. So just have that ready to use basically, but that's where it comes from. I remember at one point, I think I only actually ever like I first studied this. I didn't study it in further maths. I studied it at university, and I remember getting confused by this, probably because they just went for it so fast. But it all makes sense, I think, with a little diagram. I'm hoping it has made sense now. So we want our Cartesian equation. Right, now A is going to be this one here. This gets us onto the plane. I mean, you could use alternatives, but that's going to be the simplest one to use. So x, y, z, dotted with our normal 3 minus 10 minus 1 is going to equal that 1 minus 2, 3, dotted with 3 minus 10 minus 1. And hence, 3x minus 10y minus z is going to equal 3 plus 20 minus 3. I've just done the dot product of each of these, and that is going to give me 20. And this is the Cartesian equation of the plane. Hence, determine the value of p. So what we can do now is use this. We know, like, basically substitute this in. That can be our x, y, z. So we'll get 15 when I do 3 times 5, then minus 10p, then minus 7 times minus 1, so plus 7, and that is going to equal 20. Therefore, 10p is going to equal 22 minus 20 is going to equal 2, and p is 0.2. Finally, we're given that the lines L1 and L2 intersect at the point A. Point B has coordinates as shown, and we're asked to determine to the nearest degree the acute angle between A, B, and pi. Right, I'll come back to that. First thing I'm going to do is work out the point A, where they intersect. So when they intersect, we're going to get the x coordinates the same. So 1 plus 2 lambda is going to equal 5 plus 6 mu, minus 2 plus lambda is going to equal, remember we worked out that p is 0.2, so 0.2 plus mu, and then 3 minus 4 lambda is going to equal minus 7 plus 8 mu. And I'm just going to solve a pair of these simultaneously. So let's take the first two, and I'll rewrite this, well, keep the top one the same, and times the bottom one by, the middle one rather, by 2. So minus 4 plus 2 lambda equals 0.4 plus 2 mu. Because now I've made these the same, I can just subtract. So 1 minus minus 4 gives 5. These cancel. I've got 4.6 plus 4 mu. So 0.6. So 4 mu is going to be 0.4. Mu is going to be 0.1. Sub that back in. 1 plus 2 lambda is going to be 5.6. So 2 lambda is going to be 4.6. The lambda is going to be 2.3. It does say it's given at the intersect. I just think as part of the process, we should just check that the third one is valid. I don't think we need to write loads of detail on it, but it's actually just to help us as well, because we'll know it's correct if it does work. So I will get 3 minus 9.2 on the left-hand side. That will be minus 6.2. And over here, I'll get minus 7 plus 0.8, which is, again, minus 6.2. So great, I know that they intersect there. So point A is, I think it's easiest to use this one. 0.1 is a little bit easier to sub back in than 2.3. So let's sub it back into here. I'm going to get 5 plus 0.6, so 5.6. Got my 0.2 plus 0.1, so 0.3. And then minus 7 plus 0.8 is minus 6.2 here. And we're nearly there. So let's just draw out the plane again. We've got these two lines intersecting here at point A. Here's my position vector O. And then I've got a point B, which I don't actually know where it is. And it might not even be on the plane. well, no, it's not going to be on the plane because we're asked to find the acute angle between AB and lambda. So let's say it's up here. Now, what I need to find is AB then, or BA, but let's go with AB. So AB will equal 12 minus 11, 6, minus 5.6, 0.3, minus 6.2. This ends up being 6.4 minus 11.3, 12.2. Right, so that is our vector, and we want to find the to nearest degree, the acute angle between AB and the plane. But what I'm actually going to do is use the normal vector, because I don't have this vector here at the moment, but I do have a normal vector. So if I can find this angle, I can then do 90 minus it, and that will give me the vector between AB and the plane. And just want to remind you that the normal vector was equal to 3 minus 10 minus 1. So full on dot product now. We've got A dotted with B equals the magnitude of A times the magnitude of B times cos of the angle in between them. So I'm going to get 3 minus 10 minus 1 dotted with 6.4 minus 11.3, 12.2 equal to the magnitude of this 3 minus 10 minus 1 times the magnitude of 6.4 minus 11.3, 12.2 times cos of the angle in between. Right, we've just got a calculator for this. So when you work the left-hand side out, you actually get 120. Works out really nicely. Use 3D Pythagoras. It's going to be 3 squared plus 10 squared plus 1 squared over here. And that ends up being root 110. And this next one is really awkward. You get 17.818. 6.4 squared plus 11.3 squared plus 12.2 squared, all square rooted. And again, times by cos theta. Rearrange, this gives cos theta equal to 0.6421. Inverse cos gives theta is 50.0488. Just a reminder, that was that angle there. So we want this angle. So angle between AB and pi is going to be 90 minus that, 39.951, which becomes 40.0 degrees. Well done.